Here's a resistor, and if you look closely at it, you can see it has four colored rings around it. We call those four colored bands. And notice the way I'm holding it. They're not centered, they're off-center. And so you hold it so that the bands are more to the left than they are to the right, and then they tell you what they're supposed to tell you. And what these bands tell you is the resistance of the resistor. That is as a number, say 100 ohms or something like that. The first three bands tell you the resistance, and the last one tells you something else that I'll explain in a second. So that's one resistor, and you can see this second resistor. Take a look at that. All right, what am I doing wrong with this one? I'm holding it backwards. So you're supposed to hold it this way so you can read it, so that the bands are to your left. And you can see for this one, the bands are brown, black, and yellow, and then gold. And this means the resistance of this one is different from the one I held up before. So in this lesson, we'll learn how to read that code. This is called the resistor color code. Well, first, why not just print the number on the resistor, say 1,000 ohms? Why put a code? Well, resistors are often hard to see. In this phone that I've shown you before, you can see there are a lot of them, and sometimes they get packed in behind other things. So if you print a number, it might get obscured, but if you have a colored band going all the way around the resistor, you can see it no matter how much of the resistor. As long as some small part of the resistor is showing, you can see the colored band. Resistors are often very small too, and it could be hard to read the print. So it's traditional on resistors to put these colored bands to tell us the resistance. So that's the symbol for resistor. This is what they look like in a circuit. And you've got four bands, 1, 2, 3, these three go together, and then this one, the fourth one, is separate. You always arrange the resistor so the lopsidedness, the off-centeredness, is to the left. So the bands are closer to the left than they are to the right. The first three tell you the value of the resistance, say 1,000 ohms or 1.2 million ohms. That's what the first three tell you. Then the fourth band is sometimes separated by a gap, but usually not. And that tells you what's called the tolerance. This is an engineering term, and it means how much something can be off, but still be tolerated without making things go wrong. So here, when they sell you the resistor, from an electronic parts store, you might buy a set of resistors. When they sell them to you, this fourth band will be a color that will tell you the maximum percent that this can be wrong. And if you find that you measure this resistor and this is wrong by more than the percent guaranteed here, then you can get your money back for that resistor. It's guaranteed. So, to make a code that gives us numbers, each color has to stand for a digit. And how many digits do we have in our number system? We have 10, and here they are listed. Now, the colors follow a logical arrangement. And in a normal year, I would have you memorize them. This year, it's a nice thing to memorize them, but I can't enforce that. And the logical arrangement of this is something that makes it easy to memorize. It's not automatic, it's not automatically obvious, but it's easy to memorize. So it starts like this. Zero, for zero we use the color that means no color. When there's no light reflected from an object, that object would be black. So the color black stands for zero. Then at the opposite end, the farthest away from black, we put its opposite. What if all colors are reflected from a surface? White means 9. Now for these two, you do something close to each. Here, a 1 is represented by the color brown, and an 8 is represented by the color gray. Then in the middle we have 6 numbers, and here we put the colors of the rainbow in order. Now you might have memorized that the rainbow is Roy G. Biv, and there's an I in there for indigo, but that's 7. We only need 6, and so we leave out indigo. So 2 is red, and then orange for 3, right? Red, orange, yellow. Roy G, so green, for 5. Biv, so blue, for 6, and violet, or purple, for 7. Okay, and I've seen, when you look at resistors, I would describe this color more as violet than purple. It's a lighter color, closer to a pinkish than to a deep bluish purple. So that truly is violet, so that's a good letter for that. So this is your color code. Each color stands for a digit. Black here for 0, because that's when no color is reflected off a surface. 9 at the other end, that's when all colors are reflected. Brown is kind of close to black, and brown is a color that's not in the rainbow. Gray is a mix of black and white. It goes next to white. Also, gray and 8 have the same vowel sound. White and 9 have the same vowel sound. So if you need to memorize this, it's not that hard. And then in the middle, we need 6 colors. So we put the rainbow, Roy G. Biv, but there's no indigo, so it's like Roy G. Buv. So it's not too hard to reproduce this from memory if you have to, or figure it out. If you're an electrical engineer, when you're looking at the resistor, you can figure it out quickly. Resistors come in a wide variety of resistances. It's easy to buy resistors from a range of 1 ohm of resistance to 100 million ohms. You might think, wow, 100 million ohms, that must be really big or expensive. And the answer to that is absolutely not. It's actually very easy to make a resistance of 100 million ohms. The resistance of, say, plastic here is very, very large, much larger than that. The resistance of the lead in a pencil, take this much lead, we might get a resistance of tens of thousands of ohms, and it's really graphite. It's a form of carbon. So it's actually very easy to make a big resistance, and they're very cheap, sometimes a nickel a piece, or if you buy in bulk, even less than a nickel a piece. It's actually difficult to make a 1 ohm resistor, to make a resistance that small and make it correct. All right, so we need to be able to cover this range of resistances, 1 to 100 million ohms or even more. And we have 3 colored bands to tell us that. So let's see what the code is, how that works. So you have a resistor and you have 3 bands on it. The first band tells you the first digit of the resistance. So for example, if the resistance were 200,000 ohms, the first band would be red, a 2 for 200,000. Right? The second band tells you the second digit of the resistance. So for example, if you had a resistance of 470, this would be yellow and this would be violet, 4 and 7. All right, now think about what the third band tells you. If the first band tells you the first digit and the second band tells you the second digit, what would the third band tell you? You can pause the video and think about it. The answer cannot be the third digit. This cannot tell you just the third digit. For example, if you had a resistance of 257, red, green, violet, that could not be correct. You could not do that. So pause the video and think about why that's true. Think about what this third digit has to tell you. Right? It cannot tell you the third digit because what would the highest resistance be that 3 digits could tell you? If that did tell you the third digit, what would the highest resistance be? What would be white, 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 999? And that means you could not even represent a resistance of 1,000 ohms, but we have to get up to 100 million ohms. So this third digit here, you've probably figured it out by now, it tells you the number of zeros to add. In other words, times 10 to this here. It tells you it's called the multiplier digit. This is a true number, that's a true number, but this is the multiplier. You're multiplying times 10 this many times. Or another way of saying is you're adding this many zeros, multiplying times 10 to this. All right, so with that in mind, let's do some examples. I put the digits up here again. Remember, we have 3 bands. And for the first one, I'm actually writing the colors on the board, but I'm not going to keep doing that. I don't have every color, and sometimes it's hard to see through the video. All right, so brown, black, red. In fact, you should pause the video and try all these on your own. So now I will do them straight through with no pauses. Brown is 1, black is 0, and red does not mean 2. It means you add 2 zeros, because if this were truly a digit, we could not write a resistance big enough. So this means add 2 zeros. So 2 zeros. That's the first hurdle to get over, is to get used to that idea. So this is 1,000 ohms. And for the homework, you need to know what K means. So this can also be written as 1 K ohm. K means times 1,000. 1 kilo ohm, 1,000 ohms. These two mean the same thing. All right, now let's do yellow, violet, brown. Yellow would be 4. Violet would be 7, and brown would be 1, but it means 1 0. So 470 ohms. Yellow, violet, brown. Right now, violet, violet, blue. 7, 7, not 6, but 6 zeros. Wow, so that's 77,000,000 ohms. For this homework, you have to know that K stands for 1,000, and we're going to add one more letter to what you need to know. 1, 2, 3, 4, 5. This is 77 million ohms. A capital M means million. Technically in metric it means mega, but that stands for million. I don't care what you do, but if you're going into science or engineering or math, you should know that means mega. So this is 77 mega ohms, 77 million ohms. 7, 7, and then 6 zeros. Brown, green, black. Now you want to pause the video and try all of these. Brown, green, black would be 1, and then 5. 5 for green. All right, and then what would black be? Pause the video and think about it. Now, if you said 0, that this is 150, that's wrong. This does not tell you the digit, it tells you how many zeros to add. So black means 0, so you add 0 zeros, so no zeros. Which means this is how you say 15 ohms. All right, so that's tricky. When you see that black there, you want to write a 0, but that third digit means how many zeros to add, or times 10 to the what. So this is times 10 to the 0, and you know from math class that means times 1. So it's 15 times 1, that's 15 ohms. Right, white, black, black is 9. That's a true digit, 9. Black here does mean 0, right? Digit, digit, multiplier. So now we multiply by how many zeros? By no zeros, 0 zeros. So this one is 90 ohms. All right, now we're going to go in the other direction. What's that capital M mean? It means million or mega. So this is 1 million ohms. It means times 10 to the 6. That's what that capital M means. So 1 million ohms. And now we have to write that in colors. So you go, this is backwards. Now you go first digit, second digit, how many zeros to add? It's not that bad. First digit, second digit, how many zeros to add? So what color is that? Brown. What color is 0? Black. And what's that? That's 5, so that's green. When you work with a lot of resistors, you start to notice brown and black are by far the most common colors. All right, because resistors often come in simple numbers like 1,000, 500, 10,000. They also come in odd values like 370, 470, 530 for reasons that is beyond the scope of this class. All right, now look at this one, 40 ohms. So that's 4, which should be yellow. 4, and then 0 is black. And then how many zeros do you add after that? Remember, you have to do the first 2 digits. You have no choice. So 0, or 4, 0, and then no zeros, so black. Now, if you look at this, you might say, wait, there's another way to do that. Couldn't I do this? Couldn't I put black first, and then yellow, and then brown? Wouldn't that mean the same thing? 0, 4, add 1, 0. Technically, mathematically, it would, but all engineers make an agreement. Do not start with black. So if you have 2 choices, you do not start with black. You point to that first digit and you start with that. You don't pretend there's a 0. It just says we would never write this as 040 for 40. Same thing on the resistor. We don't write the resistor as 040 on the color code. We start with the 4. All right, now I'll try this last one. Again, start with that color, so that's yellow. Okay, and what would we put next? Well, now we run into trouble. Everything we put here will mean something. Even if I put black here, it's going to mean 0. So I wind up writing 40. So for this one, it's impossible. It's impossible to start with the yellow for 4. Now, resistors under the value of 10 are rare, maybe not even non-existent. I think every resistor I've seen that had a resistance less than 10 has had it printed on the resistor. There are various reasons a resistor like that heats up very quickly. It tends to be big and bulky, and it has the resistance printed on it. So this is rare, but technically, if you had to represent this with a color code, you have to start with black. Black, and then yellow, and then how many zeros to add? Black. So we're going to add a little bit to our rule here. Do not start with black unless you must. If you have a one-digit resistance, you have to start with black. There's no other way to do it and follow the rules. So you're allowed to start with black in that case. But if you don't have to, if there are two ways to write it, you take the way that does not start with black. And then finally, those are the first three digits, the first three bands on the resistor. But what about this fourth band? How does that work? Well, you're learning a vocabulary word. Engineers call this the tolerance, and that's a word that's used all across engineering for how much error you can tolerate in something before you consider it bad. What this tells you is the maximum guaranteed percent error. So look at all these words. Maximum means the most that these first three can be off. Guaranteed means that if it turns out you measure this and it's worse than this guarantee, you can send it back and get your money back. It's a percent, not an absolute value, so it's not like giving you plus or minus 150 ohms. It's giving you a percent. An error means how much it can be off. Here's the code. It's a completely different code from the other one. I'd never asked students to memorize this. The most common by far resistor tolerance you will see is gold, plus or minus 5%. When I was going to school in the 1980s, we did see more silver and blanks, resistors that are worse. Brown would be for more specialized uses where you really need a better precision. And there are even more colors than this. And if you Google it, you'll see there's a whole range of colors for more precise resistors. Now you might ask, well, why not just always buy this? If these are all available and you have your choice, why not always buy this? And you might want to pause the video and think about that. Why doesn't every engineer for everything always buy the best resistor? And the answer is price, is cost. Which one do you think is most expensive? Well, this one is. So if you realize in your application you don't need the resistor to be very precise, you could buy this one and save money. If you need to be very precise, you buy that one. These days, however, silver and blank, I don't even know if they're made anymore because it's become so easy to make resistors with a tolerance of plus or minus 5% that I've only seen gold when I buy them recently. All right, here's an example. Black or brown, black, red, a very common resistor. Brown, black, red, gold. So first, what would the resistance be? So you can pause the video and try to fill out all of this. So brown is 1, black is a 0, and red is 2 zeros. So this is 1,000 ohms. Okay, and the plus or minus is plus or minus 5%. All right, so the allowed range is, well, what's 5% of 1,000? Well, the way I do that quickly is I know 10% of 1,000 would be 100, so 5% would be 50. So the allowed range is to start with that and take away 5%, or take away 50, and also add 50. So if you buy a resistor, brown, black, red, gold, and it has a resistance of 951 ohms, you cannot take it back and get a refund. That's within the allowed tolerance. That's within the plus or minus 5%. The actual value of that resistor could be anywhere in this range. That's all that the manufacturer is guaranteeing. They're not guaranteeing it's exactly 1,000. That would be too expensive. So that's the function of this, of the last band, which is called the tolerance.